Hello. Quick introductory video on conditional probability. What's conditional probability? Well, we may know part of the outcome of events are along the way, and we may need to calculate the probability given that information, that knowledge. Let's use this example. Woman goes for breast cancer screening in the UK, or women go for breast cancer screening in age groups. The initial test indicates cancer, but the test is only 90% accurate, and only 5% of the female population have breast cancer. So, question is, what is the probability that the woman has breast cancer given that the initial test indicates cancer? So there's our piece of information, the indication of cancer, and that's our condition. It's given. That's why we call it condition. So let's do the calculations for this example, and we're going to do it with a Venn diagram frequency analysis first because that's clearer. So let's start on the assumption we've got 1,000 women in our population. So if 5% have cancer, that's 50 women have cancer and 950 do not. If the test is 90% accurate, then for the 50 women, 90% of them are going to get the correct answer. So 45 of them are going to be correctly indicated as having cancer, but 5 of them are incorrectly indicated that they're not. Of the 950 women without cancer, 90% will be correctly indicated, so that's 855 that they've not got cancer, but 95 are going to be incorrectly indicated that they have cancer. So we're now going to feed those into our Venn diagram, the figures we've just got there, these figures here that we've just calculated. So my left hand set is going to be those women with cancer, so that's our 50 women, the 5 plus 45. And less obviously in the right hand set is our group where the test indicates they've got cancer. So what's that made up of then? Well, we had 45 women who had cancer and the test indicated they've got cancer. Of course, the other 5 who've got cancer, the test did not indicate they've got cancer over there, so they're over on the left. On the right hand side, we've also got 95 women who do not have cancer, but the test indicates that they do. And the remainder, the 855, are down here outside both sets. They're not in either, are they? So now we've positioned all our values, we can now look to work out our conditional probability, because what we're interested in, we're only interested in those women that the test indicates have cancer. So we're only interested in those in the green circle, and that's made up of the 45 women who do have cancer, but there's also 95 women who don't have cancer, and for all of those the test indicated that they potentially did. And if we're now interested in working out the probability that if we randomly select a woman from within that group of, how many is it? It's 45 plus 95, so it's 140 women there, yeah? So what's the probability that if I selected somebody at random from that group? Well, it's the 45 out of the total. The total in this case is 140, isn't it? 45 out of 140, and that probability is 0.32. So what does that actually mean? Well, it means that if the test indicates you've got cancer, in practice you've only got a 32% chance that you actually do have cancer, yeah, because the probability is 0.32. So that means that there's a 68% chance that you don't have cancer, even though you've indicated so on the test. So there we are. Let's have a look at this now as a tree diagram approach and do a probability analysis. Okay, so we start off by looking at whether the woman has cancer or not, and we know that 5% of the population have cancer. And if you have cancer, then the test will calculate, as we did above, that in 90% of cases will correctly indicate you've got cancer. Yeah. So the probability of that happening as we multiply those two probabilities together is 0.045. And there's our 45 women from our Venn diagram, which has an equivalent probability of 45 out of 1,000 is 0.045, yeah? And that meets our criteria, doesn't it? That one for our Venn diagram, so from our condition, yeah. We've got 4 outcomes, haven't we? The next one down, cancer but not indicated. And then we move into our groups, and that doesn't meet our criteria, does it? Then we've got, going down, we've got our group of women that don't have cancer. That's got probability 0.95. And probability that it's indicated they don't is 0.9. So we've got, there's our 855 women again who've not got cancer, not indicated as having it. That doesn't meet our condition either. But our final outcome is the women who don't have cancer, but the test indicates that they do. And our probability there is 0.95 times 0.1. There's our 0.095. And that meets our criteria, doesn't it? Because our criteria is that our condition is that the test indicates cancer. Yeah. So we have 2 outcomes on our branches, 2 branches that meet our condition. And the probability in that group, if we add those 2 probabilities in green together, is 0.140. So there's, look, there's our 140 women reappearing there. That's our total probability out of the group. Okay. Now, if we want to calculate the probability that you have cancer, given that the test indicates you have cancer, well, it's the correct group. There's our probability of 0.045. There's our 45 women, divided by the probability that you meet the condition. That's our 0.045 plus our 0.095. There's our 0.14 we talked about. There's our total 140 women. And again, there's our result, a probability of 0.32. What we've done here is prove a fundamental law of conditional probability, that the probability of having cancer here, given that the test indicates cancer, is the probability of having cancer and, yeah, there's a intersect rather, cancer and test indicates cancer divided by the probability that the test indicates cancer. So here's our condition, here's our my little summary. If we're looking for a conditional probability that we have a known outcome for an event, we're going to use this term given. We use our notation, the probability of A given B, the probability of A given B. We can work it out either as a tree or as a Venn diagram. And what I would suggest is you indicate the areas you're interested in either by underlining them or using a particular colour. So those are the 2 there, or here's our set here, and then we do our calculations. It's the probability of entirely meeting the 2 criteria we've got here, cancer and test indicates it, divided by our total. Yeah, and we could do that either way from above, or we can go straight to using our probability formula. Probably the Venn diagram is the most obvious one to use, most intuitive. So I hope that's of use. Goodbye.